Good afternoon, all of you, and welcome you to the 8th lecture of this series. Today's first lecture topic is gas and ice giants, Jupiter and Saturn, Uranus and Neptune, and beyond, by Dr. Vrunda Mugundan, National Center for Earth Science Studies, Tirunelveli. And the moderator of today's first lecture is Dr. Ashwini. I will just introduce Dr. Ashwini. Dr. Ashwini is an active researcher in the field of atmospheric aerosol science. She completed her PhD from the Space Physics Laboratory in VSSC in 2021. After receiving the Chief Minister's postdoctoral fellowship from the Government of Kerala, Dr. Ashwini is now working as postdoctoral research associate at the National Center for Earth Science Studies in Tirunelveli. Over to Dr. Rishitosh.
Thank you, sir. Good evening, everyone. I would like to introduce the speaker for the session, Dr. Vrunda Mugundan. Dr. Vrunda is a DST Inspire faculty working in the field of planetary aeronomy at the Atmospheric Science Division of National Center for Earth Science Studies, NSIS, in Kerala. She received a PhD from the Space Physics Laboratory at the Vikram Sarabhai Space Center in 2019. Her doctoral research focused on the upper atmosphere of Saturn's moon Titan, marking the first systematic investigation from India into Titan's atmosphere. She secured the ISRO postdoctoral fellowship after that, and she conducted the research on Martian upper atmosphere and ionosphere. She received the Inspire Faculty Fellowship Award by DST in the year 2020, and currently she is involved in the Inspire project centered on exploring the variability of the Martian ionosphere at the National Center for Earth Science Studies in Toronto. Dr. Mugundan collaborates with numerous national and international institutions specializing in space physics research for her investigations on the Martian ionosphere. She has authored multiple research articles that have been published in prestigious international journals and also serves as a reviewer for various academic publications. With this brief introduction, I welcome Dr. Vrunda to give today's lecture. Over to you, Vrunda.
Thank you, Dr. Ashwini, for the introduction. So let me share my screen first. Okay, I hope the presentation is visible. So let us begin. So a warm good evening to all of you. So today I would like to discuss with you about some strange worlds in our solar system. If you are someone who likes to travel a lot, you might have got the experience that at some places you would feel very much like home, very much comfortable. Whereas at some other places, the things would be distinctly different. The conditions will be totally different from what you are used to or what is existing at your native place. So such sort of places exist in what we experience on our planet Earth. So such worlds we call as unearthly worlds, which means not like Earth. So here I'm showing an overview of the solar system. You can see the sun, the 8 planets, and the regions like the Kuiper belt and the Oort cloud. So if you look into the planets in our solar system, you can very easily notice that there is a significant difference in sizes when you compare the outer planets with that of the inner planets. So the 8 planets in our solar system clearly classifies into 2 groups, namely the terrestrial planets and the Jovian planets. So the terrestrial planets includes the inner planets Mercury, Venus, Earth, and Mars, and the Jovian planets include Jupiter, Saturn, Uranus, and Neptune. So apart from the sizes, there are several parameters in which there exist differences between these 2 groups of planets. So here I have shown a table in which the different properties of these 2 groups are compared with each other. The most significant difference between the 2 groups of planets is in their composition. These inner planets are mainly composed of rocks and metals, or we say they are generally rocky planets. Whereas if you look into the Jovian planets, they are primarily composed of the gases hydrogen, helium, and hydrogen compounds. So by hydrogen compounds, I mean those molecules which contain hydrogen as an element. For example, methane. So methane is CH4, isn't it? So hydrogen is there. Again, ammonia, NH3, again hydrogen comes. Then water, H2O. So all these are hydrogen compounds. So the Jovian planets are primarily composed of the gases like hydrogen, helium, and the hydrogen compounds. So since they are composed of these lighter gases, their densities are lesser as compared to the terrestrial planets. The terrestrial planets, as I said before, are composed of heavy rocks and metals, because of which they are having a higher density. So Jovian planets has got a lesser density as compared to the terrestrial ones. Also, they are far away from the sun and also far away from each other. So in short, we can say the Jovian planets are those planets which lies at the outer region of the solar system. They are enormous in size, are composed mainly of the gases hydrogen, helium, and hydrogen compounds, and hence have a lower density. And also they are farther away from the sun and farther away from each other as well. But now the question is why this sort of two kind of composition exists in the planets within our solar system. You might have already learned from the previous speakers that all the planets formed from the same solar nebula, which is solar nebula is nothing but just a cloud of dust and gas. So if every planet formed from the same solar nebula, why this sort of differences existing in the composition? Let us understand. So the main reason for this difference in the composition is the fact that the Jovian planets formed at a larger distance from the sun. So let us look into the planetary formation process. So this planetary formation starts, as I said before, from the solar nebula. The particles of the solar nebula starts solidifying through a process called condensation. And this solidified particles gradually grows in size with time until the gravity start pulling it together into a planet. So whatever that is the ingredient or the content of the solar nebula is what you should be finally seeing in the planet. So here I am showing a table in which I have listed the ingredients of the solar nebula. The nebula is primarily composed of the gases hydrogen and helium, which constitutes about 98% of the total mass of nebula. The second dominant constituent is the hydrogen compounds, which, as I said before, includes H2O, CH4, and methane, ammonia. Ammonia, NH3. And this hydrogen compounds constitutes about 1.4%. And the remaining portion is constituted by rocks and metals. And these two components together constitutes only less than 1% of the total mass of the solar nebula. So it is with the condensation of these ingredients of the solar nebula that we finally got the planets in our solar system. But the thing is that this hydrogen and helium gas in the nebula can never condense because they requires extremely low temperatures for the condensation to occur. And such sort of low temperatures not existing in our nebula. So this means that this hydrogen and helium stayed in the form of gases itself within the nebula. Whereas the other three ingredients of the nebula can condense whenever the temperature is appropriate. So the metals condense at relatively high temperatures of 1000 to 1600 Kelvin, and rocks require a little bit lower temperature for condensation to occur, and the hydrogen compounds condense at extremely low temperatures of around 150 Kelvin. Now, if you look into the solar system, you can see that at region close to the sun, the temperatures are really high, which is obvious, isn't it? Because sun is a very hot body, and those regions which lies closer to the sun will obviously be at higher temperatures. But as you go farther and farther away from the sun, the temperature gradually decreases. So you can imagine a border line between the planets Mars and Jupiter. So this border line is usually referred to as the frost line or the snow line. In the region within this frost line or snow line, that is very close to the sun, because of which the temperature in this region is very high. So that planetesimals from which the planet formation occurred within this region formed was mainly from rocks and metals, because at these higher temperatures only these two ingredients of the solar nebula could condense. And these two ingredients, as I said before, constitutes only a very small fraction of the nebula. And hence, the planetesimals from which these planets were formed were of very small in size and finally ended up as the small-sized terrestrial planets. But the scenario was different at those regions beyond the frost line, because at this region, the temperature is very low. The temperature is low enough for the hydrogen compounds to also condense in addition to the rocks and metals. So again, as I mentioned previously, the hydrogen compounds constitutes a larger fraction of the solar nebula as compared to the rocks and metals. So this means that the planetesimals from which the giant planets formed in this particular region of the solar system were much more massive as compared to the planetesimals from which the terrestrial planets formed. So more massive means they are having a very high gravity. And what happens when the gravity is very high? It would be able to capture a large amount of materials from the surroundings. So these planetesimals were so massive that they captured a large amount of hydrogen and helium gases from the surrounding solar nebula. And these hydrogen and helium gases are very light. And when a gas is very light, the thing is that it would be able to easily escape the gravitational pull of a planetary body. So that is why you don't get to see hydrogen and helium gases much in the inner planets. But in the case of outer planets, the gravitational pull was so high that even these lighter gases couldn't escape from these planets. So finally, these planetesimals ended up as the giant planets with a gas mass surrounding it. And interestingly, these giant planets do not have a solid surface, unlike the case of terrestrial planets. So on Earth, we have a solid surface, isn't it? So that is where we stand on. But in case of these giant planets, that sort of a solid surface is not there. So giant planets are basically like you have a planetary core, which is composed primarily of the hydrogen compound, rocks and metals, where the hydrogen compounds is constituting a larger fraction, and this core is surrounded by a swirling mass of gases. So now I hope you understood why we have this sort of two kind of composition among the planets in our solar system. Now the question is again whether all the four planets in the outer solar system are similar in composition. That is, as I said before, again we have four planets within the Jovian category. So whether all these four planets having the same composition? No, it is not so. So if you look into the Jovian planets itself, you can see that Jupiter and Saturn are much larger in size as compared to Uranus and Neptune. In terms of composition also, there are differences. The Jupiter and Saturn we usually refer to as gas giants based on its composition because they are primarily composed of the gases hydrogen and helium. Whereas Uranus and Neptune we usually refer to as the ice giants. So ice giants because, as I said before, their planetary core contains a large fraction of the hydrogen compounds. And these hydrogen compounds are in the condensed form. And in the condensed form, we refer to this hydrogen compounds as ices. So that's why Uranus and Neptune are considered as ice giants. So within the Jovian planets itself, you have two subcategories based on its composition. The first one is the gas giants, which includes Jupiter and Saturn, which is composed primarily of hydrogen and helium. And the second category is the ice giants, which includes Uranus and Saturn, which again is composed by the hydrogen compounds along with rocks and metals. So you will find something interesting if you look into the density of these planets. So I'm talking about density because we are discussing about the composition, and the composition is ultimately what determines the density of a material, isn't it? So what is density? So density is nothing but mass per unit volume. And it is this particular parameter which decides whether a body will float or sink if you put it into a liquid like water. So water is having a density of 1 gram per centimeter cube. So if the density of the body is greater than that of 1 gram per centimeter cube, it will sink in water, otherwise it would float. So here I have shown a chart in which the density of the different planets in our solar system are indicated. As you can see, the terrestrial planets are having a higher density, which is obvious because they are composed of heavy rocks and metals. But the Jovian planets are having a lower density because they are made of lighter elements like hydrogen and helium. And among the Jovian planets, Saturn is the one which is having the least density. Density of Saturn is even less than that of 1. That means if you can find a water body which is large enough to hold our planets, and if you put Saturn into it, the Saturn will float. So now we discussed so far about how we had two different type of composition and how we categorize the planets into two groups based on this composition. And our focus is on the Jovian planets. So now I would like to discuss about some interesting features of this Jovian planets, which makes them very intriguing bodies in our solar system. So one such feature is their ring system. So whenever you get to see a picture of Saturn, you will always notice this beautiful ring system around it. So it is hard to even imagine Saturn without its ring system. Actually, not only Saturn, all the other three Jovian planets also has got this ring system. But they are not very thick or shiny as a Saturn's rings. So that is why they are not very easily detectable. And this ring system look like a solid sheet from Earth. But actually, it is not a single solid sheet. It consists of many consecutive rings which are separated from each other by narrow gaps. And these consecutive rings are composed of small pieces of rocks and ices which goes around the planet like tiny satellites. Now let us understand how this ring system forms around this Jovian planets. The main reason for the formation of the ring system is the enormous gravity of these planets. As I said in the beginning, these Jovian planets are very gigantic because of which they are having a very large gravity. And there is something called Roche's limit. So Roche's limit is the distance from a planet within which if you put another celestial body, such as a small satellite within this region, the gravitational pull that is experienced by the celestial body from this parent planet will be enormously high so that it will disintegrate itself into small bits and pieces. And these bits and pieces will finally start going around the planet, ultimately flattening into a disk. So this is how the terrestrial planets develops a ring system. And sorry, Jovian planets develop a ring system. And so again, so why terrestrial planets are not having a ring system is because of the fact that they are small in size. So this is because of which they are having a lower gravity and hence a ring system did not form around them. So that was about the ring system. Now coming to the satellite system. So again, if you look into the terrestrial planets, you can see that we only have three satellites within the inner planetary system. So one is our Earth satellite, which is Moon. Then Mars has got two satellites named as Phobos and Deimos. But this is not the case if you look into the Jovian planets or the giant planets. Currently, we know around more than 285 satellites for all the Jovian planets. And the Jupiter and Saturn are the one having a large number of satellites. Each of them has got more than 60 satellites. So here I have listed some of the prominent satellites of the Jovian planets. The first four shown over here are the satellites of Jupiter. These four are usually referred to as the Galilean satellites because they were discovered by the scientist Galileo. And each of these body has got its own intriguing features. For example, if you look into Io, so Io is the most geologically active body in our solar system. So there are a large number of volcanoes on the surface of Io, and the eruptions in these volcanoes are so frequent. And coming to Europa, Europa is an icy world. It consists of an icy shell. And now the scientists are almost sure that there is a very large ocean of water beneath this icy shell. So this body Europa has become so intriguing that now NASA is going to have an exclusive mission for studying Europa. The mission is named as Europa Clipper mission, and it is going to be launched in coming October, that is October 2024. Then Ganymede. Ganymede is the largest satellite in our solar system. And coming to the satellites of Saturn, there is a very interesting body called Titan. So Titan is the largest satellite of the planet Saturn and the second largest satellite in our solar system. And the interesting feature of the Titan is that it is the only satellite in our solar system which has got a thick atmosphere. Its atmosphere is even thicker than that of Earth's atmosphere. And in addition to the atmosphere, it has got many other interesting features like There occurs volcanic eruptions, tectonic activities, then wind, methane cycle is there, liquid bodies are detected on the surface of Titan and all that. So each and every satellite in our solar system, I mean, now in the outer region of our solar system are very intriguing bodies. They have many features which are similar to those of a planet, but because of their small sizes, they are considered as satellites only. Now, the next aspect of the Jovian planets, which I would like to touch upon, is their atmospheres. So all the four Jovian planets has got very thick atmospheres. And these atmospheres are primarily composed of the gases hydrogen and helium, with a considerable fraction of the hydrogen compounds as well. So Jupiter and Saturn almost has got similar composition, with the difference that in Saturn the abundance of helium is lesser as compared to Jupiter. Whereas in case of Uranus and Neptune, hydrogen and helium itself are the abundant compounds, but there is a higher abundance of hydrogen compounds, especially methane, as compared to the gas giants Jupiter and Saturn. So even though methane constitutes only a minuscule fraction of this atmospheres, it is this particular gas which is virtually responsible for almost all aspects of its physical appearance. So if you look into Uranus and Neptune, you will always notice that they appear in shades of blue. So this occurs because of the presence of the methane gas in their atmosphere. The methane absorbs the red wavelength from the incoming solar radiation and scatter back only blue light. And that is the reason why these two planets appear in shades of blue. Again, in these atmospheres of the giant planets, as I said before, there is a significant amount of hydrogen compounds, especially methane. And the presence of methane in these atmospheres initiate a very interesting chemistry, which we usually refer to as the methane photochemistry. We call it photochemistry because the chemistry is initiated when incoming solar radiation interact with the gas particles in this atmosphere. So once methane and the other gases in the atmospheres of this planet interact with the incoming solar radiation, a series of chemical reactions, complex chemical reactions sets in. And what you ultimately get as the byproduct of this chemistry is very heavy hydrocarbon molecules, atoms, ions, etc. And in these atmospheres, especially in the case of Jupiter and Saturn, the temperatures are very low that these hydrocarbon compounds could condense into the form of clouds. That is, you get to see hydrocarbon clouds in the atmospheres of Jupiter and Saturn. And these hydrocarbon clouds forms very interesting circulation pattern in this atmospheres. So we call this belt zone circulation. So if you look into this picture of Jupiter, you can see something like stripes that appear on a child's ball. There are regions of bright lines and like slightly dim lines. So these bright regions are usually referred to as belts, and these dim regions are usually referred to as zones. They are actually nothing but this clouds going around the planet. So the sort of belt zone circulation is there in Neptune as well, and also in case of Uranus, but they are not as evident as in the case of Jupiter and Saturn. Again, this giant planet atmospheres holds most of the dramatic weather phenomena, in our solar system. You get to see lot of storms in the atmospheres of this giant planet. So if you again coming back to this picture of Jupiter, you get to see this red spot in its atmosphere. This red spot is actually a very huge storm that is occurring at the southern hemisphere of Jupiter. And this storm is referred to as the giant red spot. So it's so enormous in size. You can actually fit in 3 Earths into it with room to spare. So you can imagine how big it is. And another interesting fact is that this storm has been going on for several centuries. It is not dying out. So why it is not dying out is because of the fact that, as I said before, these planets don't have a solid surface. So we know in Earth, when hurricanes or storms forms, how do they die? When they get onto the land, due to the friction, they lose their energy and finally they die out. But in case of this giant planets, there is no solid surface. So because of this, once the storms forms in the atmosphere, they last for centuries. So this giant red spot is a very large storm that is occurring in the atmosphere of Jupiter. One such storm you can see in the atmosphere of Neptune as well. It is called the Great Dark Spot. So this sort of dramatic storm events are occurring in the atmosphere of the giant planets, which make them a very dynamic system. The atmosphere is a very dynamic system for the Jovian planets. Again, one more aspect of the Jovian planets, which I would like to touch upon, is the magnetic field of this planets. So we all know that Earth has got a magnetic field, and this magnetic field look like the one created by a bar magnet. So it's a dipolar magnetic field. So similarly, all the four giant planets also has got this magnetic field. The difference is that their magnetic field is so much enormous, or they are much stronger as compared to the Earth's magnetic field. So here I have shown a table in which I have compared the strength of the magnetic field of different giant planets with that of the Earth. And you can see Jupiter is the champion. The magnetic field strength of Jupiter is around 20,000 times larger than that of Earth. And how a planet generates a magnetic field, I hope you might be knowing. It is because of the presence of molten magnetic material in its core. So in case of Earth, we have this molten rock, molten iron core, because of which we have a magnetic field around our planet. In case of Saturn and Jupiter, it is not the iron core, it is because of the metallic hydrogen core. That means in the inner core of the planet, the hydrogen is staying not in the gaseous form, but in a metallic form. It is something which you never get to see on our planet Earth. And this occurs because the pressure is enormously high in the inner region of this planet, so that the gaseous hydrogen is compressed into the liquid form. And it is this liquid hydrogen which is causing the magnetic field for the planet. Again, because in the liquid state, what happens, the electrons are not closely attached to the nucleus. So the electrons are free to move. So electrons are free to move means what? Current is generated. And when current occurs, there will be a magnetic field. So this is how the magnetic field forms around this giant planet. Again, Uranus and Neptune also has got a magnetic field around it. But in this case, it is not the liquid hydrogen core which is creating this magnetic field. Instead, it is the core of the hydrogen compounds that is causing the magnetic field. And this magnetic field creates a space or large cavity around the planet, which we refer to as the magnetosphere. So magnetosphere is actually the region around a planet within which the magnetic field of the planet dominates over the magnetic field from the sun. Or we say the planet's magnetic field dominates over the interplanetary magnetic field. So here I have shown a comparison of the magnetospheres of the four giant planets. And as you can see, the Jupiter has got the largest magnetosphere within the giant planets, which is obvious because it has got the strongest magnetic field. And because of the presence of this magnetic field and magnetosphere around this planet, you get to see auroras on these planets as well. So you might be already knowing how auroras are created on Earth. So it is because Earth is having a magnetic field around it. So when charged particles are coming from the sun, this charged particle enters into the Earth's atmosphere through this magnetic field line and collides with the atmosphere in the high latitude region. So when these charged particles interact with the gas particles in the atmosphere, there occurs wonderful display of colors in the sky. So that is what we call as auroras, isn't it? So the same sort of thing happens in the atmosphere of giant planets itself. There occurs auroras, especially in case of Jupiter and Saturn. You will get to see a lot of picture in Google if you browse for auroras on Jupiter and Saturn. So far we touched upon some of the interesting properties of the giant planets in our solar system. So how do we get to know all this information about the giant planets? So there are different methods for studying planets in our solar system, isn't it? We can do telescopic observations, or we can do theoretical studies like modeling and etc. However, the best way to study any planet is to send a spacecraft to the planet. So let us see which all spacecraft have visited our giant planets. So here I have shown a table in which I have listed the name of all those planets. I'm sorry, all those spacecrafts which have visited the giant planets of the solar system. So as of now, eight spacecraft have entered into the realm of the giant planets. The Voyager missions were flyby missions. And this Voyager missions made flybys with all the four giant planets, Jupiter, Saturn, Uranus, and Neptune. And Voyager had flybys with all these four giant planets. And what is a flyby? So flyby means the spacecraft is not getting into an orbit around the planet, but it just making quick click of the planet as it is moving forward. So that is what we call as a flyby. But to have a detailed study of a particular planet, we need to have orbiters, which are spacecraft which goes in orbit around the planet. So coming to the orbiters of this around this giant planets, we had three orbiters. So one is Galileo, the next one is Cassini, and the other one is Juno. So Galileo and Juno are missions for studying Jupiter. So Galileo mission got over, and Galileo had got a probe which was released into the Jupiter's atmosphere. So during its descent through the Jupiter's atmosphere, it made in situ measurements of the Jupiter's atmospheric parameters. Again, Juno is again a mission for studying Jupiter, and it is currently operational. So it is now currently it is going in orbits around Jupiter, making observations of the Jupiter's parameters. And the Cassini mission was actually a mission meant for studying Saturn. So we call it as Cassini-Huygens mission. So in Huygens, this Huygens actually indicates a probe. So Huygens was actually a probe which was released into the atmosphere of Titan, the Saturnian moon Titan. And the Titan, just like the Galileo's probe, descended through the Titan's atmosphere and made in situ measurements of the parameters. And like there are upcoming missions like JUICE. JUICE is again another mission which is designed for Jupiter. Then there are missions for outer solar system satellites like Europa Clipper, which I already mentioned in previous slides. There is going to be another one which is called Dragonfly, which is again a mission for studying Titan, the satellite Titan. So these all are the missions which have visited the outer solar system planets and which have told us much secrets about the outer solar system planets. So now it is almost like we discussed about how we had two groups of planets in the solar system, why their composition is different, and what are some interesting features of these planets. Now let us see what lies beyond the orbit of Neptune. So does our solar system end with Neptune? No, it is not so. Beyond Neptune, you will get to see something called the Kuiper belt. So Kuiper belt, I have already shown this picture of Kuiper belt and Oort cloud in the first slide. So Kuiper belt is like a big icy donut that is lying beyond the orbit of Neptune. And this Kuiper belt is composed of a large number of icy stuffs or icy particles, which we refer to as Kuiper belt objects or KBOs. So you know Pluto, right? So Pluto is an example of a KBO. So long back, we used to consider Pluto as a planet, but it lost its planetary status when scientists identified that Pluto is just one among those lots of KBOs that are going around, going in orbits beyond the orbit of Neptune. And humanity have just started exploring this Kuiper belt. And so far, only two spacecraft have entered into the region of Kuiper belt. One is the Pioneer mission, but the Pioneer mission didn't make any observation of KBOs. And then we had this New Horizons mission from NASA. So New Horizons was a mission, actually it is still an ongoing mission. So New Horizon mission was designed for studying Pluto and its satellite Charon. So Pluto is a KBO, as I had mentioned before. So New Horizons made a detailed study of the KBO Pluto and is currently continuing its observations in the outer regions of our solar system. Now, beyond the Kuiper belt, actually, I shouldn't say it's beyond the Kuiper belt. There lies something else as well called Oort cloud. So Oort cloud is something like a spherical shell that covers our entire solar system. So our solar system lies as if it is sitting inside a bubble created by this Oort cloud. So Oort cloud again consists of many icy materials, especially those of comets. So you might have heard about long period comets. So Halley's comet, you might have already heard about. It's a long period comet. So long period comets are those comets which take more than 200 years to complete one orbit around Sun. So those sort of long period comets actually comes from this Oort cloud. So we actually haven't made any physical observation of this Oort cloud yet. But from calculating the back trajectory of the long period clouds, I mean long period comets which are visiting our inner solar system, scientists guess that they should be a space like Oort cloud from which this comets are coming. So this Oort cloud still remains as a partial mystery which needs to be explored further. So with this description of the Oort cloud, I come to the end of my presentation. So it is like we have almost reached the farthest end of our solar system. But remember, this is like I have just touched upon many aspects of the outer solar system planets, and there is much more things to explore. So my basic intention was to spark your interest so that you can delve into the further details of this outer solar system planets. So keep exploring. Thank you.
Thank you, Dr. Vrinda, for this very informative session on the gas and ice giants of our solar system. We are now ready to take up questions. So I request the participants to post their questions in the chat box. Okay, we have one question from Balaji. Why does the magnetic field of Earth is 1?
Okay. Actually, the magnetic field of Earth is not one. I think you got this question because I showed a table in which I have listed the magnetic field value as one. That was just for a comparison purpose. That it is like what I wanted to convey there was if you take the magnetic field strength of Earth was as one, then the magnetic field, what would be the magnetic field strength of other planets? So it is not like the magnetic field strength of one. Magnetic field of Earth is one. I just put it for representative purpose only.
Okay, we have another question. Uh, does the water beneath the Europa's icy surface get tidal effects due to Jupiter?
Obviously, it will be having tidal effects. Actually, any satellite in our solar system will be experiencing tidal effect from its parent planet. So that is why because of which they are able to stay as satellite around the planet. So Europa will definitely be experiencing tidal effect from Jupiter.
Okay, we have some more questions on Jupiter. Why is it called a Jovian planet? And then, is it possible there is a solid hydrogen core? Uh, how is it possible that there is a solid hydrogen core in Jupiter?
I actually said, okay, before that, somebody asked, like, what is a Jovian planet? So, Jovian means, the word Jovian means Jupiter like. So, Jovian planets actually refers to the outer planets in our solar system. So, initially, everybody thought that when our science was not advanced as it is now, everyone thought that, like, all the four planets in the outer planets in the solar system is much similar to Jupiter. So, then people started calling it Jovian planets, which means like Jupiter, the planet like Jupiter. So that is what Jovian means. Now the other question was, Ashwini, can you repeat the question?
Yeah, like why is there a solid hydrogen core for Jupiter?
Okay, Jupiter doesn't have a solid hydrogen core. What I said was that core of this Jovian planets are made up of three elements primarily. The first one is the icy compounds, icy hydrogen compounds, which are the condensed form of the hydrogen compounds. The next thing is the rocks, and the third one is the metals. And the abundant thing is the hydrogen compounds. And it is not like the solid hydrogen core. What I said during my presentation is that it has got a liquid hydrogen core. So that means liquid hydrogen core means the hydrogen gas is put into such a high pressure so that it changes from the gaseous state to a liquid state. So this is something which you never get to see in Earth because that sort of high pressure never exists on Earth. So in Jupiter, you have this liquid hydrogen core, not the solid hydrogen core.
And also like why the moon has a solid surface, moon of Jovian planets, why they have a solid surface. So the question is like why they don't have a same surface as the planet, as the hot planet. Why moon have a solid surface?
I think the question is how the Jovian planets, I mean, Jovian satellites got to have a solid surface while the Jovian planets don't have that.
Itself is a yes.
So it could be because I am not a geologist, but I think like it could be because this satellites actually retain this. When what we call as a satellite is actually the core from this satellites formed. They couldn't capture much of the gases from the nebula, so that is why they couldn't end up as the gas giants like our planets. So they couldn't capture much gas from the solar nebula because of its lower gravity. So only that core remained. So that core is what you get to see as the satellites.
Okay, we have another question like whether the Oort cloud is considered as a boundary of the solar system. Whether it is
We can't
like a
say it's like a boundary. You don't have well-defined boundaries when you talk about space. So Oort cloud is like a very large bubble, as I said during the presentation. It's like a large spherical bubble. So you can consider it as a boundary of the solar system. As of now, we consider that that like it is the outer reach of our solar system, I should say, not as the boundary.
okay. So Prince Kumar Singh has a question like whether in future whether Earth will get any type of ring structure like Jupiter or
I think it
Saturn.
is largely unlikely because, as I said, this ring system forms when the gravity is enormous, and the Earth is a terrestrial planet, and it has got that much of it doesn't have that much of gravity to hold a ring system.
Okay, I think we have answered all the questions. Is there any more questions? Okay, I think then we can conclude this session. So thank you everyone. Over to you, Praveen sir.
Thank you, Dr. Brinda, for this informative and very inspiring lecture, taking us to the outer planets and also now its moons. Very informative. Thank you so much for sharing your knowledge with us.
Thank
and
you.
I also would like to thank Dr. Aishwini for nicely moderating the session. Thank you both. Now we will move over to the next lecture. The title of this lecture is Moons of the Solar System Planets by Dr. Rishitosh Sinha, Physical Research Laboratory, Ahmedabad. The moderator of this lecture is Dr. S. Vijayan from the same laboratory, that is a Physical Research Laboratory, Ahmedabad. And I would like to tell about Dr. Vijayan. Dr. Vijayan is working as a planetary scientist at a Physical Research Laboratory and involved in ISRO's Moon and Mars mission. And he will be giving a lecture on India's lunar exploration program on 3rd May and in our series of lectures. So he will be our future speaker also. So it may take some more time to start this lecture. Please be stay on. So we can start the session. Over to Dr. Vijay.
Okay. Thank you, Dr. Praveen, and good evening all. And it is my pleasure to introduce my friend and colleague, Dr. Rishitosh, to start this lecture. So I'll introduce him as an enthusiastic research scientist, and he works on the planetary remote sensing at the Planetary Science Divisions at Physical Research Laboratory. He's a researcher and interested in understanding the geomorphology of the planetary bodies and to understand and quantify the topographical analysis of surface process of Moon and Mars. So his research involves the extensive analysis of data from Indian missions like Chandrayaan-1, Chandrayaan-2, Chandrayaan-3, and even from the Mars orbiter missions. So it doesn't stop with that. And he has expertise in working with other countries' planetary mission data sets. To tell about his awards, he's recently awarded the Eminent Alumni Awards in Science and Technology from for 2023 from SRM University, Chennai. And all about that, he is one of the science team member and the main team member for the Chandrayaan-3 Pragyan rover mission. So with this, I welcome Dr. Rishitosh to deliver his lecture.
Thank you very much, Dr. Vijayan, for the kind introduction. And thank you, Praveen sir, and Director SPO and Director PRL for giving this opportunity to talk with the enthusiastic, younger aspirants who are very much eager to get into the planetary science and explore the planetary bodies, use the data, remote sensing data, and the in situ data that we have, and then see how not only these planetary bodies, but as well as how the moons of the solar system has evolved and how they are different from each other. So my today's talk will be actually focused on that. So I'll be sharing my screen. So I hope my presentation is visible to all. Yeah. Okay. Thank you. So as I told you, the title of my talk is basically focused on moons of the solar system planets. So I am aware that the moon is already being discussed with the participants of START program, and it has been already discussed that how solar system is formed. So, but apart from that, if you see the solar system in general, what do we see here is that there are 8 planets that are actually revolving around the sun. And among these 8 planets, we have the first 4 are called as the terrestrial planets, and then the next 4 are called as the Jovian planets. And within these Jovian planets, we have got gas giants, which are Jupiter and Saturn, and then there are ice giants, which are Uranus and Neptune. So what we are going to see today is that the solar system that we have, one of the solar system of the 500 solar systems in the Milky Way. So this solar system, our solar system, not only these planets are there, but there are so many moons which are there in the solar system. Specifically, if you see the Jovian planets, if you compare the Jovian planets and the terrestrial planets, you will find that there are so many moons in the Jovian planets, around the Jovian planets. With respect to terrestrial planets, we already know that Earth has a moon, and Mercury and Venus do not have a moon. Whereas if you see Mars, it has got 2 moons, Phobos and Deimos. But if you see the Jovian planets, starting from Jupiter to Neptune, multiple moons are there around these planetary bodies. And if we see them, totally, if you try to count them, as per the latest information that we have in hand, we can see that there are nearly 293 moons, which are surrounding these planetary bodies. So it is very important for us to basically understand how come, first of all, these giant bodies have got so many moons, what are their context with each other, context of the moons with each other around the planetary body, and how these planetary bodies have, how these moons have evolved, how the surface of these moons look like. And let me tell you all that not all these moons have been explored in detail, but there have been some missions like Cassini, Voyager, these New Horizon. These are some of those missions which have, made flyby missions around these moons. So whatever data we have in hand, we have from those flyby missions, and from that data we can, analyze the geology, geomorphology, the subsurface, the atmosphere, the ionosphere of these moons. So when I say atmosphere and ionosphere, let me tell you that there are some moons or a moon in the solar system which has got an atmosphere, and that atmosphere is denser than the Earth atmosphere. I'm sure some of you may be already knowing that, but we will see that in detail in these slides. So, but before I get into my presentation, let me tell you all that all this data that are acquired by the flyby missions, they're all there in the web, and it is freely accessible. So anyone interested in exploring these moons can basically analyze, make use of this website, and they can analyze the data. Like you see here, all the moons of Saturn, majority of moons of Saturn for which we have flyby missions, all the moons of Jupiter, Neptune, and Uranus, the data sets are available. When I say data sets, it means images, spectroscopic information about the subsurface. All these are present. So anyone interested in this can make use of this particular feature present on web. And if you find any difficulty in downloading the data, you can contact me. I've given my email ID below. So let us first start with the moons that are there, that we see around Jupiter. So if you see Jupiter, there are 4 moons. There are many moons actually, there are few moons which are actually in the inner orbit, which are very close to the Jupiter. But then there are many moons which are slightly further from the, or you can say, the outer orbit of Jupiter. And out of these moons, there are 4 very peculiar moons. They are called as Galilean moons because this has been observed and discovered by Galileo. So this is Io, Europa, Ganymede, and Callisto. So among these 4 moons, Io, the one which is always in news, it is actually one of the most curious objects in the solar system. How do I say that? Why? Because it has got plenty of features that makes it different than any other moon that we have in the solar system, and we will see how it becomes so intriguing. And you see, these are the innermost moons. So what do you see here? I'm showing you the relative size comparison. So you can see Io is slightly bigger than Europa, but it is of course smaller than Ganymede and Callisto. But when you see the orbit of Jupiter and the moons that are surrounding it, not only that there are these Galilean moons, there are several other moons. We have just seen that how many moons are surrounding these Jovian planets. So you see so many orbits you can see. So, but these are very far away from these Galilean moons, and they are like very further, so they crisscross and all those, but they do not come closer. So when they do not come closer, although they may be having some gravitational pull from Jupiter, but as far as these Galilean moons are concerned, they are highly influenced by the gravitational influence of Jupiter itself. So when you see Io, it orbits very close to Jupiter at a distance of 350,000 kilometers above the Jupiter's cloud tops. So if it is so close, when you see Jupiter from the surface of Io, you will see that it is actually 39 times bigger than our own moon. So you can get a size comparison. The moon that we see in the sky, and if you are on the surface of Io, and if you look at Jupiter, it will be like 39 times bigger than our moon. So you can see how close it is to Jupiter. So you can now imagine that being close to such a huge planetary body, what type of effects may be ongoing on this Io. So one very peculiar thing that happens on Io is, the orbit. There is a term called as orbital resonance. So the orbit of Io is actually in sync with the two of the other moons. So you can see the relationship here. Ganymede, by the time Ganymede makes one orbit around Jupiter, Io makes 4 orbit around Jupiter. Whereas when you see Europa, by the time it makes one orbit, Io makes 2 orbit around Jupiter. And because of this, there is always a sort of gravitational influence on the moons. And because of the moons that are Ganymede and Europa, they exert gravitational influence on the Io. And that basically never allows it actually always enhances the eccentricity of Io. And when you see how it influenced altogether with the gravitational influence of Jupiter, you can see when the Io is actually revolving around Jupiter, it is undergoing it is under an experience of heavy gravitational influence from these moons and the Jupiter itself, and because of that, there is bulging of Io all around. So this bulging is so peculiar that you will see tides that are rising up to a height of 100 meters, and that is not very common. If you see on moon, it is very simple. The effect of tidal influence on our own moon, or because of on Earth, because of the moon, is very less. It is higher, slightly influenced. But when you see Io, it is highly influenced by the gravitational pull of Jupiter as well as the orbital resonance that is there with Europa and Ganymede. And as a result of that, what do we see? We see that there are volcanoes that are erupting on the surface of Io. And these eruptions have been captured by New Horizons in 2007. And I think this is the most intriguing thing that I have ever seen in planetary science, where one can see that the jets that are coming out from the plume, we can say plume that is erupting from this particular place on the surface of Io, as well as you see that there are surfaces on the surface of Io which have changed over time. So you see, if you compare these two images taken by Galileo over the course of 3 months, you can see that there are regions which can reveal evidence of shifting of lava flow. You see, initially it was here, but then it enhanced and it is here. So you can make us understanding from here that Io is one of the planetary body or the moon which is actually having an active volcanism. So having an active volcanism on a moon, isn't that very surprising? It is. It is very much surprising that we have, because these planetary bodies do not have tectonic plates. So despite of that, they are having such volcanic activities ongoing on the surface. We know very well that Venus has got volcanic activity, but then having volcanic activity on Io is really a surprising thing for me when we talk about the moons of the solar system. This is another example in which we can see plumes erupting from the surface of Io. You can see one example here and another one here. You can see the zoomed images of those plumes. You see that there are plumes that are erupting from the surface of the Io. So it is very important for us to understand how these plumes are forming, what exactly is the composition of the material, the gases that are ejected from the interior of the Io. Are they sulfur? Because sulfur is one of the most abundant gas that comes out when volcanism takes place. So is it that, or there are several other gases that are mixed? So it is something that needs detailed exploration, and I'm sure that in future we will have some missions where we will look in more detail at Io. But then scientists have also tried to explain how these volcanism may be erupting. So there are 4 different ways in which it can happen. These are 4 different basically models. So in one case, it says it could be a solid body dissipation in the deep mantle, where we have just like crust, mantle, and core, and then because of that, we have some molten bits of magma in the interior, and that may be erupting. Then there is another concept that is solid body dissipation in the asthenosphere. So the asthenosphere is actually sitting over the molten mantle, and over time, due to the bulging, tidal bulging, the surface is fracturing and magma is oozing out. Then another concept says fluid body dissipation in the magma ocean. So just like the way we had magma ocean on moon, it is assumed that maybe in the past there was a magma ocean on Io, and then that also is oozing out in form of fluid due to the tidal influence that is there because of the Jupiter and the other moons. And then there is another one where they say that dissipation in a magmatic sponge, where below the crust of Io there are some pockets, some spongy pockets that make it look like as if little fracture is made, those sponge from those small pockets magma will ooze out, and those are called as magma sponge, which will ooze out if it gets a easier pathway to come out on the surface. So people have tried to explain these this intriguing volcanic phenomena that occurs on Io, but still it requires a lot of detailed investigation for which we need more missions in the future. The next to Io is Europa. So Europa is another very intriguing moon of the solar system. So you can see the comparison between Europa and moon. So Europa is actually not very small than our own moon, but slightly smaller. And it is the second and smallest of the 4 Galilean moons that we have. We have already seen the size comparison. Although it is second and smallest of the 4 Galilean moons, but if you see in the entire solar system, it is the 6th biggest moon in the entire solar system. So 6th biggest moon in the entire solar system, and it is so intriguing. If you see the surface of this particular moon, you will see that it is having a lot of linear features, and these linear features, although it may be not very wide, but they are several 100 kilometers long. So now you think how these fractures are forming. Are they fractures, or they are simply some sort of groove, some sort of depression, some sort of collapsed units which are there on the surface of Europa? So it is very important for us to understand, and is that linked to something which is happening in the subsurface? And along with these linear features, we also see several circular marks. So what are these circular marks? Technically, these are called as lenticulae, but how these have formed? Are they simply corresponding to the material that is coming from the subsurface and pushing the crust, and then maybe they have formed jets in the past, and now what we see them as simple circular features, or they are simply the collapsed units? So it is very important for us to again understand that how these lenticulae would have formed. And then there are a lot of chaotic features on the surface of Europa. You see, these are the chaotic features, and what we don't see on Europa is the craters. So you can see a couple of craters over here, but as such, if you see, you do not see those large craters, which makes the surface old. So you all know that whenever a surface forms on any planetary body, it will have no craters, and as it gets old, as it accumulates crater, basically it gets old. So you see in this example in particular, you don't see a lot of craters. So how it is like this? Why the surface does not have craters? Our moon has got lots of craters, but why this surface has not got craters? Or maybe the craters were there, they got erased due to some activity. So what is that activity? So these all features, make it very important for us to explore these moons. And what else we have seen with respect to Europa, that if you see the south pole of Europa, the presence of water vapor has been detected. And from where this water vapor can come out, most likely is that it could be from the subsurface. So the Hubble Space Telescope has observed evidence of water vapor, and it has been proposed that the subsurface of Europa might have some ocean, might hold water. And subsequently, later on also, you can see plume has been detected, and they have been detected around multiple years, 2014 as well as 2016. So modeling, there have been some modeling studies which outline a process for brine or salt enriched water in the subsurface of this particular moon, which moves around the moon, and eventually in some locations where there are fractures which connects with these salty water, it basically erupts in form of plumes. So that's why these moons are again having high significance when we look at the basic elements that are required for sustaining life. You need water, you need oxygen, you need organic compounds. So all these things have been basically, very promisingly, they have been observed on these moons. That is why these moons are very important. And based on these evidences, the structure of the Europa has been proposed, where it says that the lake has got an icy crust. It has a top is actually icy crust, and then it has got liquid water beneath that, and there is the rocky mantle. And what happens that because of this tidal effect, the core is actually always getting some influence, and it is always staying hot. And because of that, the water, the ice that is melting beneath is actually oozing out, and it's coming out of the surface in forms of jets or in forms of some other features that we see on the surface of Europa. So this is just one example. So here you see the water is actually oozing out of the fractures that are there on the surface. So if such a situation is there on Europa, can we think of having a sort of base on the surface of Europa where humans can survive, mankind can survive? So that's why these moons, they attract a lot of interest when we talk about exploring the possibility of having potential life on these moons other than Earth. So not only that, we are looking at the planets which are the terrestrial planets, but you see in the case of Jovian planets also there are moons which have which hold evidence of having subsurface ocean, subsurface water. So can they be useful? Can they save us? Some people say that there can be some natural calamity in the future. So can we use these moons for safeguarding ourselves? So why? Because these moons have got those basic uh, elements that are required for sustaining life, just like water. So among the other moons that are around Jupiter, Ganymede is actually another moon which is around which is next to Europa. And as we know that it is the largest moon that we know, and it is actually defined to be home to the largest ocean water. So if you compare the size of this Ganymede with Titan, it is actually slightly bigger than Titan, so 1.02 times that of Titan, and when you compare with Mercury, it is much larger than Mercury. So you see, Ganymede is bigger than Titan as well as bigger than Mercury. Being a moon, it is bigger than a planet. So, but as I told you that being a very large moon, it has also got a large amount of water. So it is actually considered as the home to the largest ocean water in the solar system. But apart from all this, there is something else that makes Ganymede very unique, in the solar system. So we will see what is that. So there is another comparison where you can see with respect to the moons, how where does Ganymede stands with respect to having subsurface water. So it is the largest, having largest water body in the solar system in the subsurface. So it's of course special, but then it is also special because it is the only moon that has got the internal magnetosphere. And what do you see on the surface over here and here is basically the aurora that has been spotted on Ganymede. So the first question is that how can this particular moon can get magnetic field? And then the presence of aurora. So I am sure that you all know that auroras occur when the charged particles that are launched along the magnetic field collide with the particles in the atmosphere. So typically auroras form at that point of time. But how do we see it around Ganymede? You can see here, it has been observed, Hubble space has seen presence of aurora. So there is a concept that tells that probably there is something that has to do with the presence of, because having aurora on Ganymede and having a stable aurora on Ganymede is actually something very peculiar. So it has been proposed that probably that there is a salty ocean, which basically makes this stability, that the aurora in the atmosphere of Ganymede is stable. It doesn't wobble a lot, although it is very close to Jupiter. It doesn't wobble a lot. Okay, but as such, if you see, it has got relatively older darker regions, The darker regions that you see are these ones, and then there are lighter regions. So the darker regions are old, larger craters are preserved in the darker regions, and younger regions are the lighter regions are the younger regions, which are dominated by grooves and ridges. And these grooves and ridges are again very high standing ridges. So then along with an old surface, we have a young surface, and the young surface is dominated by grooves and ridges. So how come we are seeing all these features on these moons? Something that is happening beneath that, or something that is happening externally on these moons that is actually modifying the surfaces of these moons, because you see very contrasting surface. One is very old and one is very young. So that type of combination is very intriguing for me. And based on these intriguing observations, the geological maps have been also prepared. So you see the detail of these maps, to what detail they have been interpreted and identified and mapped. So this tells that the level of confidence that we have in terms of exploring the Galilean moons that we have in our solar system, at least the Io Europa and the Ganymede. So this boosts, this also boosts my confidence, to look at the datasets of these moons and then see how different are these morphological features, geological features with respect to the geological features that we see on Mars, Moon, Venus, Mercury. So because why these are very important, because this will tell us that already we know that there are some planetary bodies which have preserved old surfaces, but then here we see that there is an old surface as well as a young surface. So it is very important to understand how these different surfaces have formed over time. And this particular planet moon is one particular moon which you can analyze, you can study to get insights into the basically active processes that happen in these Jovian planets. Apart from Io Europa and Ganymede, there is another moon which is called as Callisto. So Callisto, if you see, has not been talked. People do not talk a lot about Callisto because they think that it has got nothing to do. It is a very boring surface. It is a very old surface. So why do we talk about Callisto? But being an old surface, an old surface has got a lot of significance. Why? Because you will not get old surfaces on Earth, or because Earth has got plate tectonics and Earth has got so many other phenomena that old surfaces are replenished on Earth. So if you want to study old surfaces, and it is considered as one of the very old surfaces, in the solar system, the surface is 4 billion year old. So getting a surface which is 4 billion year old will definitely tell us a lot of information, will provide a lot of information about the processes that occur during the formation of the solar system. That is the early epochs when the planetary bodies, the other planetary bodies of the solar system are formed. So all those secrets are basically locked in on the surface of Callisto and the subsurface of Callisto. So if we can get access to the high resolution data of Callisto, one can make out how these different phenomena are there and how these older epoch events are there when the solar system formed. So you see, if you compare the diameter of Mercury and Callisto, again there is a very slight difference. It's just a few kilometers smaller than the Mercury. And then when we look at some of the high resolution pictures that we have of Callisto, one very important thing that we see here is that the surface is of course very highly cratered. But then when you see the rims of these craters, you see this is a crater, and you see the rim of the crater. When I say rim, it means that raised surface around the circular feature. So you see the raised surface is highly fractured or highly weathered or highly muted. So what is happening here? Why these features have broken apart? I see a lot of gaps between them. Even you see majority of these circular features, they appear like very eroded, or you can say very like disturbed. So how that has happened? And then there are some which are still, we can see the boundary. So what is this happening on Callisto? So can we explain this? So one of the explanation is that probably there is subsurface CO2 ice, which is actually sublimating and causing these, erosion. So because of that sublimation, the ice is sublimating and it is creating void spaces. and due to that, the materials are collapsing and forming these eroded surfaces all around the craters. And that is varying in time. There are craters which are still intact, there are craters which are eroded. So over an old surface, which is 4 billion year old, we see differences in the events of the activities that are happening on the surface of Callisto. So this is something very intriguing. So an old surface showing us signatures which are of that old time, as well as the event that is connected to the present day, that is the sublimation of CO2 ice. And then there are some other features also. You see this is a large crater, or you can say a basin, and then you see below also you see several fractures that are formed on the interior of the crater. So this could be a signature of possible sublimation of ice from the interior. And then there are very intriguing features where we see that lots of knobs kind of features are formed. These features are conical features. So again, the question is that how are these forming? Here as well as you see here, in both different, density is different in both the images. So can we have an explanation? We can try it. Maybe it is likely that these could be again some leftover rims of the several craters that formed over time, but we cannot explain such dense population of this, because this type of thing we have not seen generally in the other planetary bodies that we often look at, like Moon and Mars. But you see here you see an intact crater, and then I see several eroded remnants, and then here the density is so high. So these things make Callisto very intriguing. And as I have shown, you might be noticing that these things are not there in any of the other moons, any of the other Galilean moons. So that makes it very different. And you see, not only craters, there are large multi-link structures also. Like this is one example of a multi-link structure called as a Valhalla, which is there on the surface of Callisto. So that's why I'm asking this question, that will Jupiter's moon save us? So there is a notion, there is a science fiction that maybe these moons have got some basic ingredients or the essential ingredients that is required for sustaining life. So the question that I pose here is that will Jupiter's moon save us? Can we make use of the resources that are present in the subsurface of these moons and then make a sense whether we can really stay there? Okay, so take that on a lighter note, but yes. Then coming to Saturn. So what do you see here is, this is the example of Titan. Titan comparing with the other moons of Saturn. So you see here, Titan is the largest moon of Saturn. And when the moment I talk about Titan, I sort of get goosebumps, because Titan is one of those moons which have been explored by instruments made by mankind. I am sure you may be knowing about the Cassini-Huygens probe that landed on Titan. So this is one of those moons which have been explored. And the two other aspects that makes it very unique is that Titan has got an atmosphere. Titan has got an atmosphere which is relatively denser than the atmosphere of Earth, and Titan is the only moon where we see this evidence of surface liquids. Whether it is water or some other form of liquid, that is still a question of debate, but there have been observations that there are surface liquids on this surface of Titan. So that's why Titan becomes very interesting in terms of exploring, first of all, exploring it and understanding how it evolved, and then exploring with respect to understanding signatures of past life. This is again a size comparison, because this is very important when you are looking at the moons. You have to understand how big is the moon, where it is actually, the context is very important. So you can see Titan is actually slightly smaller than Ganymede and bigger than all other moons. But if you just keep Ganymede and Titan side by side, you may think that no, Titan is actually bigger. Ganymede is not the bigger one. But the truth is that Titan appears to be relatively big because of its thick atmosphere. The thick atmosphere is so thick that it goes up to several hundred kilometers, and that makes Titan relatively appear to look relatively bigger than Ganymede. So Titan's, the vertical atmospheric structure is somewhat similar to what we see on Earth. So Earth as well as Titan, they both have got troposphere, there is stratosphere, there is mesosphere, and there is thermosphere. So if you see in particular the troposphere of Titan, you will see that at somewhere around 32-kilometer altitude from the surface, there is a presence of methane clouds. And then as we go further above, you will see the presence of tholin haze. So tholins are basically, it represents a wide variety of organic compounds which are expected to form by the solar ultraviolet or cosmic ray irradiation of simple carbon containing compounds. So when these are irradiated, carbon containing compounds can be carbon dioxide, it can be methane, it can be ethane. So when these are irradiated, tholin is formed. So it basically represents that particular class of compounds. So that is there at an altitude of somewhere around 120 to 140. And then as you go further above, you see a detached haze layer, which that haze layer is found at a altitude of 450 to 500 kilometer. And as we go further, we see that there is a event of particle production in the thermosphere of Titan. So this basically was concluded when Cassini made a closest approach, and it measured a large amount of heavy ions and particles. So that gave us a clue that there are some particle production phenomena happening in the thermosphere of Venus, Titan. And here what I show is the three different views of Titan taken in three different wavelengths. So the first image is actually a natural color composite, which is a combination of images taken by the three filters that are sensitive to red, green, and violet light. And here it shows what actually Titan may look like when we see with the naked eye. And the second one is the monochrome image, where we see Titan at a wavelength of 938 nanometers, which is a near infrared wavelength, and that allows to see the hazy atmosphere which is around Titan. And then the last one, which is the false color composite, here we see combination of two infrared images taken at wavelengths of 938 and 889 nanometers with a visible light image taken at 420 nanometers. And here what do we see? The green areas is actually those areas where we are able to see down to the surface. The red areas represents the areas which are high in the Titan stratosphere, where atmospheric methane is actually absorbing the sunlight. And the blue areas actually which we just seen as the detached haze layer. So these are the three different layers that we see very promisingly on the Titan using these three multiple wavelength images. And as I told you that there are evidence of surface liquids on the surface of Titan. So you see these are the radar images. So the areas that appear smooth, that are smooth, appear to be dark, and you see these smooth areas have got are there. It can be seen on the surface of Titan. And when we see the smooth areas in the colorful view, you can see that they have got very good drainage patterns. They have got very good drainage network. So these drainage networks are very common when we see on the drainage water body on Earth. So that's why it resembles that it could be none other than surface liquids. And interestingly, it has been observed that over time, when you see from 2007 to 2015, these surface liquid bodies have actually undergone change. You see this particular feature, it has actually evolved over time. You see, you can see materials flowing away from this particular feature, and then again it is intact. So such changes have been also observed on the surface of Titan. So it is very important to see why these features are actually happening. And then some more observations where presence of vortices have been also observed, as well as the clouds have been observed. So all these phenomena have been observed with respect to exploring Titan. So all these phenomena makes evident that these moons are very significant in terms of understanding the intricacies of the solar system and why they are showing such different characteristics. And one of the reasons you can think that we have seen till now Io, Europa, Ganymede, Callisto, and why they do not show evidence of surface liquids. So one of the reasons that we see evidence of surface liquids in case of Titan is that it is actually immersed in the magnetosphere of Saturn. So probably because of that, it is preserved from the radiation, that high energetic particles that are coming in the solar wind. So probably because of that, the atmosphere is intact and the features on the surface are preserved. It's not lost as in case of Mars. You know that Mars has a thin atmosphere, we don't see surface liquids on the surface of Mars. But here in this case, maybe because of since it is immersed into the magnetosphere, it is likely that it is protected, and that's why we see such particular features on the surface of Titan. The other very interesting moon is Enceladus. It is interesting, because when I saw some of these animations, I could notice that there are some jets that are coming out of these, moons from the surface of this moon, and these jets have been referred as icy particles, burst of icy particles from Enceladus. So, as I showed you Io, that volcanic eruption, now you see eruption, the plumes that are forming because of the jets of icy particles. So how can this happen on a moon? What the interior of the moon is made up of? So I really, get very much fascinated when I see such types of features from around these moons. So definitely Mars, Moon, and even our Earth have got a lot of, intricacies, lot of secrets, lot of mysteries. But then you see these moons; they have more mysteries. So we should have more missions, more missions sent to these moons, and then see. We should immerse, just like how Cassini immersed into the plumes, and when it immersed into these plumes, it found basically that these are basically none other than water vapor plumes. And you see this extent of these jets. These jets are 40 times the size of Enceladus. So now you can think 40 times the size of Enceladus, that huge amount of jets, are being erupted from the surface of Enceladus. Probably these jets are erupted from these features, which are called as trigger stripes. So these are linear fractures, which may be, oozing out water by a process something like this, where it is said that because of the tidal effect, the core gets heated up and it basically melts the ice, and it basically oozes water from beneath, and that not only water as well as some organic compounds as well, and that all goes up, interacts with the icy crust, and then again goes out in form of these plumes. So along with these plumes and along with this direction of water vapor by the Webb telescope, phosphorus has been also discovered, in the Saturn's moon, Enceladus. So when I say phosphorus, it is the very essential building block for life, and that has been detected in Enceladus. So you see how relevant are these moons when we talk in terms of exploring the signatures of life, exploring this possibility of having a life or on these planetary bodies, maybe in the past or in the present. So that's why these moons I have been telling that they are very important for detailed exploration. Coming on to another moon, which is the Miranda, which is actually Uranus moon, and you see Miranda is actually located somewhere here if you compare with the other moons. So it is the closest one, and it is basically the innermost of Uranus' 5 round satellites. So Miranda, Ariel, Umbriel, Titania, and Oberon. It is the innermost one, and this is the only high resolution image we have, because it was only once that Voyager 2 probe could actually take up the close-up images of Miranda. But nevertheless, although once, but what we have seen that the surface is highly, it is like very complex surface. You can see a lot of features. You can see a 20-kilometer high scarp is there. How high is Olympus Mons? On Mars, it is 23-kilometer high, but that is a volcanic mountain. Here we see a scarp, which could be tectonic, and that is having a height of 20 kilometers. So then how it could have formed? It's very much intriguing that how can such a high standing scarp can form on such a moon. So that tells a lot about the active interior of these planetary bodies, and not only active, extensively active interior. Not only that, there have been some other tectonic evidences, like these are polygonal craters. So these polygonal craters, they typically form when there is a pre-existing fracture at place. So because of presence of a pre-existing fracture, you may get these linear shapes, or they may end up forming these polygonal. Circular feature may end up becoming polygonal. So such type of impact craters have been also seen on Miranda. And you see several other intriguing geological features are seen on the surface of Miranda. So the question that becomes important is again here is that how they could have formed. And you see another example here where I'm comparing the muted craters that are formed on Miranda, and how does it compare with the other moons. So these are all the evidences which propels us to explore these moons in detail. And one another moon that is there is Triton, which is of Neptune, and particularly one particular special aspect of this particular moon is that orbit is retrograde. It means it doesn't rotate in the way the planetary body is revolving. So it is rotating in the other direction, opposite direction. Okay. So based on that, it is proposed that Triton could be a captured Kuiper belt object, because not all the moons have formed the way our moon has formed. Some are captured as well. So it is proposed that Triton could be a captured moon of Neptune. And the surface of Titan, if you see, it shows that it doesn't have a lot of craters. What does it signify? It signifies that it is capable of resurfacing itself. And if at all craters have formed, they might have get erased over time. So that ability to resurface is uncommon in the solar system. And it is again an indication, because these are icy moons, icy bodies. So it is an indication that the interior may be still warm. And if the interior is warm, as we have seen in the previous cases, water and all those fluids that are there in this interior may ooze out in form of jets or in form of plumes. So you can see how significant these moons are again. And there are other features as well. When I just told you about plumes, so you can see plumes have been, of course, observed, and geysers have been observed on the surface of this particular moon. And there have been several models that have been used to explain how these geysers and all those plumes may be forming. I think I'll skip this given that time is limited. But if you also see, there have been evidences for formation of cryovolcanism. You see, these are two volcanoes that are present. So these are cryovolcanoes. Cryo means ice. So they are having some sort of mud or mixture of mud and lava, those type of signature, or it can be relatively more mud than other features. So these features are also being spotted on this particular moon. And then coming to the one of the other moon, which is around this dwarf planet Pluto, which is this Charon. So Charon is very special again, because if you look from an astronomer point of view, it is the Pluto and Charon system. They are actually called as binary system of planets, where, as in the previous cases, what we have seen that the moons are rotating around the planetary body. But in this case, it is not rotating around the, not only rotating around Pluto, but they actually make a binary system. So what happens that instead of Charon orbiting around the Pluto, Charon and Pluto orbit around a gravitational point between these two bodies. So there is a gravitational point between these two bodies, and there are several observations which has, New Horizon has also seen that it's not simply rotating around Pluto, but actually there is a gravitational point between these two bodies around which it rotates. This is just another example which signifies the binary system of planets. And you see the other moons that it has got 4 other moons: Hydra, Nix, Kerberos, and Styx. So these moons, they are also again not simply rotating, but you see they are rotating around the gravitational point between these two bodies. So you see how these moons are rotating. I have a video which can show you how somehow these are not running, but you can see how this particular Nix is actually rotating around the Pluto. And it is said that the sun might rise in the west on next and set in the east on one day, but in some other day the sun might rise in the east and set in the north. So types of intriguing aspects have been observed with respect to the other moons of Pluto than Charon. And of course the surfaces, again we don't have a full coverage, but still we see that there are canyons. These are very large canyons which are there on the surface of Charon. I had a video actually to show you how actually we can see the canyon, but the video is not running unfortunately. And then the surface is having a very high elevation. You see, there are surfaces which are 6 kilometer high. So this signifies the presence of that deep canyon, because you have two high surfaces and in between there is a low surface. So this is the canyon that goes through. This is the canyon. So how can these canyons have formed? We know on Mars that there have been several geological episodes which led to the formation of valleys minors. But how do we see such canyons on Charon? So then, not only that, there are several tectonic features. Graben is there, ridges are there, scarps are there, grooves are there. These are tectonic landforms which are there. So is this moon tectonically active? Does it have plate tectonics? It's of course a very challenging thing to ask, but then how do we see these features? So I think again I had a video, but it's not running. So I'll quickly end by summarizing about Phobos and Deimos. So these are the two other moons of Mars. Along with Mars, these two moons are very significant. You see again, these are the this is basically the orbit of Phobos and Deimos. So Phobos, as you see, Phobos is relatively larger than Deimos, and Phobos is closer to Mars than Deimos. And our own Mangalyaan, Mars orbiter mission, has also observed Phobos. You see, this is a short animation showing the transit of Phobos over Venus, so over Mars. Since MOM had an elliptical orbit, it could capture this particular view. And then another example in which you see Phobos passing in front of Deimos. And you see the surface of Phobos, you can see grooves on the surface, and there are several craters in chain. So how come these grooves and this crater is called a Stickney crater? How this particular crater has formed, and why these grooves have formed? Are they related to the impact cratering process itself, or they have formed subsequently? You see, one side is having so much groove and one side is not having grooves. Why? Why is it so? So these are the questions that makes these moves very relevant. And here also I wanted to show you that transit of Deimos over Sun, and this was taken by one of the rovers that are there on the surface of Mars. So what we have learned today? So we have learned that there are among the Galilean moons that are there, we have seen that these Galilean moons are very significant when we talk in terms of exploring the presence of subsurface ocean, subsurface ice, and all these things on the neighboring gas giant, the Jovian planets. And not only that, our moon holds several secrets, several mysteries. These moons that are there around the Jovian planets, they also hold a lot of mysteries. They have got, some of the moons have got dense atmosphere, some have got internal magnetosphere where auroras have been spotted. Presence of liquid has been seen on the surface. Then we have seen some of the moons that are volcanically active, and we have seen some of the moons which are very old, 4 billion year old surfaces are there. And then along with that, we also see moons that has got both old and young surfaces. And then we also see moons which are not old, the surfaces are very young. So all these combinations today we have seen, and I'm sure that the attendees of today's lecture will definitely go and look at some of these moons. Using I have already shown you how we can download the datasets. So I invite you all to get into this domain of planetary science and look at these different datasets of these different moons and try to see how these moons have evolved, how the surfaces have evolved. Okay, I think I'll end here. Thank you very much for giving this opportunity. Yeah, so I can take up questions. So, Dr. Vijay. Let me know if there are any questions.
I'm just waiting for questions to be posted. Yeah, there are a lot of questions. Okay, the first question is about Titan. What atmospheric constituents give yellow color to Titan?
What atmospheric constituents?
Yeah.
Let me straight away go to Titan. So one of the things that we see in Titan is actually it is nitrogen rich. So that's why it is more, more considered to be more relevant with respect to the exploration of atmosphere. So the atmosphere is having high amount of nitrogen as well as methane. So I think around 98% of the atmosphere is having presence of nitrogen, and the remaining is methane.
Okay. The next question is, are there any possibility that these colonies or access are occupied by any creature?
Yes, I think this is something which keeps us motivated that there that we are not alone in this universe. There may be some creatures not like us, but there may be some life forms. Maybe in the past, if not present, they actually occupied these surfaces of these moons. Because when you see that these surfaces are so intergrowing, it is very reasonable to think that some form of creatures would have definitely evolved or survived in this particular on the surfaces of these particular moons.
Okay. The next question is like, is it possible to build artificial atmosphere as Titan for Earth for protecting the harmful UV rays?
Okay, so this is a very challenging question as well as something which I think I will leave it to the person who has asked this question, because if he or she has got some very intriguing idea by which we can build artificial atmosphere, then of course we can definitely discuss more about that.
Yeah, you mentioned in some of the satellite bodies, there are some linear structures and chaotic terrains. So what is the source for that?
Okay, so simply said, the linear structures can be fractures, and how these fractures are forming. If those fractures are there on some of the Galilean moons, then as I told you that these moons are under orbital resonance with the other moons, except Callisto, Ganymede, Europa, and Io under effect of orbital resolution, and then they are also under the effect of gravitational influence from Jupiter itself. So that can lead to the formation of fractures, and when there is a tidal heating, the ice that is there in beneath these moons, they may melt and ooze out, and they may subsequently widen these fractures. So that is one possible way by which we can explain these fractures.
Okay. So other question is like, for Earth, most of the water was brought by meteorites. So how the outer region of the solar system has large amount of water, what was the source of water molecules to get formed there?
So it's again a very interesting question. But whatever I have learned, whatever I have read through materials, the source may not be very much different than what we see for Earth. It has to be comets. It has to be some of the asteroids that probably delivered water. Because why I can say that, because craters are the most important, most dominating features. Even if there are surfaces which have undergone modification, but initially they should have craters. So if that is the case, then comets are one of the primary sources that would have brought water, delivered water to these moons as well.
Yeah, I think the session will keep on going. If more questions are taken, I'll just hand over to SPO for concluding the session.
Thank you, Dr. Rishitosh, for this inspiring lecture.
Thank you very
And,
much, sir, for the opportunity.
yeah. Actually, we have learned a lot of, lot of information on these outer planets as well as its moons. Very informative. And also, I would like to thank Dr. Vijayan for nicely moderating the session also. And of course, Vijayan will be addressing again this community in a different role as a speaker. I think Vijayan will be addressing on May 3rd. And also Rishitosh also will be a future speaker in a different session. So we will be meeting both of you again in this session. Thank you, both of you.
Right, sir. Thank you very much, sir. Thanks to all the participants who are basically attending this lecture. Thank you all.
Participants. So the same time, 3:30. Thank you. Bye-bye.